This last part of 5.2 is going to introduce a very special base. So this very special base is called the number e. And it's a super special number in mathematics because this guy, Leonard, now I always say this wrong, I think it's Euler, but I always want to say Euler. But he named this number e and he found it. And it's kind of a number like pi, where it's a number that does not terminate, it does not repeat, so it's irrational, and it's a constant. So e is logged into your calculator. There's an e button, which we'll explore in a second, and it's equal to 2.7182818284, blah, 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 blah. This e base, so something that we haven't talked about yet is when you have a base like 2, this is telling you that your whatever you're talking about is doubling over time. So we are going to be using applications in 4.6, and so the x will represent time and y will represent something, maybe population over time or something like that. And so when you have a base 2, that means that you're going to double. You know, after an hour you've doubled. After 2 hours you've doubled and doubled, so you've quadrupled, and so on and so forth. Well, what Leonard Euler found out was that things don't double in nature. They don't triple, they don't half. They actually grow continuously. And so this natural base E represents continuous growth. So that's more than you need to know right now, but I think it makes it relevant. And so we are going to learn how to graph and interpret graphs of exponential functions with a base of E. So the first thing I want to do is just practice plugging these numbers into a calculator. So I've brought up my calculator here, which is going to be very different than your calculator. Okay, so this is like the computer calculator, but I've got an E, right? Everybody should have an E. It's very different than an EE, which is exponential notation, or an EXP, which is also exponential notation. It's an E. So I just have to hit E and my E comes up. So then you can see that 2.71828 blah, 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 blah. But if I wanted to do an exponent, so most calculators make you put an exponent. So to get this number, you would have had to put E1. Or for me, I have to go e to the exponent 3, right? And that's e to the exponent 3. So this is, to 4 decimal places, 20 point, oh, now I've lost it. What was it? 20.0855. So 0855. Okay, what if I put it as e to the negative 0.23? Negative equals. You get 0.79, I just can't remember, 0.7945. What about e to the 0? You get 1. Anything to the exponent 0 is 1. All right, so let's look at some features of these graphs base e. Well, what's the asymptote? Well, it's still y equals 0. What's the domain? It's still negative infinity to infinity. It still has a range of 0 to infinity. It still has a y-intercept at 0, 1. Just because it's a base of 2.71 blah, 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 doesn't make it any different than any other base which is greater than 1, right? So 2.71 is greater than 1. This is an exponential growth graph. Okay, so now what we want to do is we want to graph y equals e to the negative x plus 3. Again, if you were the textbook, you would write this as e to the 3 minus x, and you'd go left 3 and then reflect. Personally, I like to do them in order, so I'm going to factor out that negative, and this is what I'm going to graph. So I'm going to have a base graph of y equals e to the x. Now, to graph y equals e to the x, it's not easy because it's not perfect numbers. I can have a perfect number at 0, 1, but from there, when I put in x is 1, I get 2.71, somewhere here. When I put in x is 2, I get, I think, 7 point something. Let me just see. If I plug in e squared, I get 7.389, so 7.4. So it's going to be here 7.4, somewhere up here. Okay, so it's steeper than a y equals 2 to the x graph, but not as steep as a y equals 3 to the x graph, and then it is approaching the asymptote. Now, what about my transformations? Well, this tells me that I'm going to, first off, reflect what values? Well, the negatives with the x, I'm going to reflect the x values over the y-axis. And maybe I do that first. And then the second thing I would do is take that and move it right 3. Okay, if you're the textbook, you'd go left 3 and then reflect it. I'm doing it this order. So I'm going to reflect my x values. This point's going to stay the same, and then I'm going to move it right 3. This point here, 2.71, I'm going to reflect it, so it's going to go over to here, and then I'm going to move it right 3. 1, 2, 3. Then I could take this point here, I'm going to reflect it in the x values over the y-axis, then I'm going to move it right 3. 1, 2, 3. I get this shape that looks like this. And again, if you're not comfortable with transformations, feel free to do a table of values. Maybe you'd know to start, like if I was doing a table of values, I would plug in maybe x is 3 to start, and then maybe put a 4, maybe put a 2, maybe do some more within there, but solve for the y values, okay? Or you can do it as transformations. Did the asymptote change? Nope, still y equals 0. Domain? Pretty repetitive, negative infinity to infinity. Range, I didn't reflect it in the y values, so it's still 0 to infinity. And the y-intercept, well, let's plug it in. So y equals e to the negative 0 plus 3. I always plug it into the original. This would be e to the 3, which we discovered above was 20.0855. So if I look, this is a good way of checking if I've graphed correctly. This graph would keep going. So my next point past here would be somewhere up here, which I'm guessing would be at y equals 20.0855, but I don't have to actually graph it. All right, welcome to E.